Hey everybody, welcome to lesson 1.3, graphs of equations. What we're going to do today is graph standard types of equations, find intercepts, symmetry, zeros, extrema, and average rate of change. This should be, again, familiar to you, but this is going to be really good review. This is going to provide us a foundation to work off of for the rest of the year. You should already know slope-intercept form, along with probably most of the lesson going into this lesson. Our essential question is, how do we graph equations and interpret them? And one example of something that you will be able to do is describe increasing and decreasing behavior of a function in interval notation. So I'm going to pause right now to pull up the notes. Here we have the notes for graphs of equations, lesson 1.3. As always, make sure that you're writing your own version of this, either online paper, or make sure that you printed this out ahead of time so that you can fill it in. Either way works, but you will have to submit this at the end. So first up, we have a lot of definitions, almost a whole page. So if you're writing this online paper, feel free to summarize. You don't have to write every word. But first up, we have a linear equation. This should be a review. Our M, remember, means slope, and our B means y-intercept. We're going to get into some different types of equations though today, including quadratic. So quadratic looks like this in standard form, and the curve opens up when a is positive, and the curve opens down when a is negative. And there's something called a vertex, which if the curve opens up and it looks like this, the vertex is right there at the base. The lowest point on the graph. If it was upside down, then it would be the highest point. That's the vertex. And the x value of the vertex is always negative b over 2a, which is kind of interesting in this form, but it is true. And there is a large proof as to why that is that we're not going to be able to get into today. For absolute value, the standard form looks like this, and h and k are filled in, but x and y stay as they are. And h comma k is the vertex here, and a is the slope. So absolute value usually looks like some sort of a V shape, right? So the vertex would be this same point right here, similar to the quadratic. And the slope, if a is positive, this part has the right slope, but over here, it's kind of like a negative version of the slope, because it's absolute value, so it bounces back up. If the a was negative, it would be facing down instead. This is a standard form of an equation of a circle. Again, h and k are filled in, and this time r is also filled in. X and y stay as they are. And h comma k, instead of being the vertex this time, is the center point of the circle. And r is the radius of the circle. Make sure you write that form of the equation down, because we're going to come back to that. Intercepts. So whenever we're looking at an equation, x-intercepts happen when y is 0, and for y-intercepts, x is 0. There's three types of symmetry that we're going to look at here. There is x-axis symmetry, y-axis symmetry, and origin symmetry. And that type of symmetry defines the line of symmetry, right? So x-axis symmetry means that we're reflecting over the x-axis, and that's what these ordered pairs are describing. If x comma y is on the graph, x negative y is also on the graph. So there's this point above and below the x-axis that's reflected. For the y-axis symmetry, we're on both sides of the y-axis. So if we're over here, we're also over here, and that's what that ordered pair describes. And origin symmetry is the weirdest one. It's symmetry about a point, and the point is, in this case, the origin, so at 0, 0. So if we have 1, 2 on the graph, -1, -2 is also on the graph. It reflects about the origin. So the x and the y actually both switch signs for that one. And again, we'll see more examples of that as well. Zeros. 0 is just a fancy way of saying the values of x for which f of x equals 0. In other words, the x-intercepts, aka meaning also known as x-intercepts. We're going to look at the vertical line test a little bit. If the graph of a function, if a graph is of a function, any vertical line will touch the relation at one point at most, which we looked at a little bit already, but we'll look at that more. We have a relative minimum, a point with the lowest y value in the close vicinity, and a relative maximum, a point with the highest y value in the close vicinity. And these last ones are already typed here. We have the average rate of change. Rate of change is just a synonym for slope. So if it's an average slope, it's a slope found using the slope formula given two ordered pairs on a curve, and that's the average slope between those points. So if we had a slope like, or a curve like this, from here to here, if we find the slope of the line that connects those 2 points, that's the same as the average slope between those 2 points. And then we have two types of functions. I wasn't super familiar with these terms before this course, so I'm not sure if you were, but function can be called either even or odd, and that correlates to its type of symmetry. So an even function is a function where opposite x values yield the same y values, and that's the same as y-axis symmetry. And an odd function is a function where opposite x values yield opposite y values, or origin symmetry. And it's called even or odd because of the highest exponent of a polynomial that would have this type of symmetry. So like an x squared function, for example, would be even. It will have y-axis symmetry if you think about a parabola. And x cubed would have origin symmetry. If you think about, the curve goes up and down in the first quadrant and the third quadrant. And so that's going to be your origin symmetry. I'll draw it in case that's not clear, like this. Something like that, right? That might be kind of small, but hopefully you can see it. Okay, we're going to keep going. So example 1, linear equations. Determine whether the following points lie on the graph of y equals 10x minus 7. All right, so this really isn't too bad, I hope. We have an x value and a y value. We're going to plug it in, see if the point's on the line, okay? So we have the y is 13. 10 times the x is 2, minus 7. So we have 13 equals 20 minus 7. 13 equals 13. That is true. So we are on the line. For the second one, we'll do the same thing. We have an x value and a y value. We'll plug it in. So I get negative 3 equals negative 17. That is not true, right? Cross that out. So this point is not on our line. And that, I think, brings up a really good point, that a line, when it's defined with an equation like this, y equals 10x minus 7, it's just a series of gazillion points, of a gazillion points in a row. It's really just saying this line is just a ton of points all lined up right next to each other to make this line. And we can zoom in really far, and it will always look like a line because there's always more and more points. There's an infinite amount of points on that line. It's kind of a weird way to think about it. All right, so that brings us to example 2. Quadratic equation. So letter A, find the vertex of y equals 2x squared plus 8x minus 3. So if you remember from the beginning of the notes, we have this equation negative b over 2a to find the x value of a vertex that's given to us in standard form like this. So in this case, the b is 8 and the a is 2. And when we start to reduce this, we'll get negative 8 over 4 or negative 2. So our x value is negative 2. And then to find the y value of the vertex, all we do is we plug negative 2 in for x and see what we get. So we're going to have 2 times negative 2 squared plus 8 times negative 2 minus 3. So negative 2 squared is 4 times 2 is 8. Negative 2 times 8 is going to give us negative 16, and then minus 3. So we're going to get negative 11. And so our vertex is at negative 2 comma negative 11. Okay, for letter B, again, we're going to find the vertex, and this time the equation looks a little weird. If we rewrite it with a 0x, we get x squared plus 0x minus 2. So our A is 1, our B is 0, and our C is negative 2. So if we go to an x value of negative b over 2a, we're going to get negative 0 over 2 times 1. So we get 0. And for our y value, we plug in 0 for x. So it's going to be 0 squared minus 2. So we get negative 2. So this time our vertex is at 0, negative 2. And for letter C, now we're actually going to graph. So we're graphing the equation that we just found the vertex of. So we know that the vertex is 0, negative 2. So what I usually do is if I'm going to make a table and it's a quadratic and I have a point that's the vertex, that should be the center point that I'm plotting here. So 0, negative 2. And I'm going to go just kind of up 2 and down 2 from there. You know, this is not a precise science or sequence of events that I'm going through here. I'm just doing what I usually do. But this will work. So if we plug in negative 1, we'll get negative 1 squared is 1, minus 2 is negative 1. Negative 2 squared is 4, minus 2 is 2. 1 squared is 1, minus 2 is negative 1. 2 squared is 4, minus 2 is 2. So I plot all of these points. And then I graph it. It should look like a very nice parabola. So there you have it. That's what we're graphing there. All right, next up we have intercepts. We're going to find the x and y intercepts for each equation. So first up, I'm going to plug in 0 for y so that we can find the x-intercepts. Subtract 4, and we'll go negative 4 equals x. So we have an intercept at negative 4 comma 0. And then I need to plug in 0 for x and solve for y. So we have y squared equals 4. And I'm going to square root both sides. Now, this is important. Whenever I'm the one that initiates a square root, which I'm going to do right now, I have to write plus or minus in the answer. Because technically, 2 squared is 4, but negative 2 times negative 2 is also 4. So we write this as 0, comma 2, and 0, comma negative 2. There's all of our y-intercepts. So on the graph, if we plotted those, the curve would go through those points, and that would be our y-intercepts and our x-intercepts, right? So let's try letter B. All right, so for this first one, it's not as simple as just solving for x because we have an x cubed term and an x term. So I'm going to factor out an x from both because that's the greatest common factor. And then x squared minus 4 is a difference of 2 squares. You might remember that that can factor to x plus 2 and x minus 2. And that gives us 3 different intercepts, right? Because we have each one of these factors now can be set equal to 0 individually and solve for x. So this first one means that x can equal 0. The second one means if I subtract 2, I would get x equals negative 2. And for the third one, if I add 2 to the other side, so I guess I'm imagining an equation here. I guess I can write that down if that's helpful. It's like x minus 2 equals 0. I'm adding 2 to the other side to get x equals 2. So the 3 intercepts that are coming from this are 0, 0, negative 2, 0, and 2, 0. And then we're going to do the same thing, plugging 0 in for x. So we get y equals 0 cubed minus 4 times 0. So y equals 0. And that's 0, 0. You might notice that's the same ordered pair we got over here. That's because that origin is an x-intercept and a y-intercept. So 2 and 1. Pretty fancy stuff going on here. And that brings us to example 4. Symmetry. Find the line of symmetry for each equation below. All right, so I'm going to use the graphing calculator to take a look at the graph so we can see if we can guess the line of symmetry. So let's see if I can find a spot here that doesn't have a glare. That looks pretty good. So I'm going to type in x squared minus 2. Graph that. All right, pretty standard parabola. And if I had to guess right now what type of symmetry this is, remember what that means is, where is there a line that I could fold and the curve would match up on both sides of the line? And if I had to guess, I would say right here, the y-axis looks like a pretty good guess for a line of symmetry. So we can test that theory if we go to the table. My table is messed up from before, so I'm going to switch it back to auto. There we go. I'm going to scroll up and down here, and let's see. So if it is y-axis symmetry, if x comma y is on the graph, negative x comma y is also on the graph. I'm pulling that straight from the beginning of the notes. So we have negative 4 comma 14. So if I switch the sign of the x value, the y value should be the same. And it is. And that's going to be the same for all of these. This is not a proof of symmetry, but this is a good way to approximate or estimate symmetry. And that's enough for us. So we're going to say that the y-axis is the line of symmetry here. Okay, let's take a look at the second one. Y equals x cubed minus 4x. And you know what? Just to be clear, I'm going to write a couple examples of the ordered pairs just so that we can see how it's changing. All right, let's take a look at the next one. X cubed minus 4x. Okay. All right, this one's a little trickier. It does not look like y-axis symmetry, right? If I folded along this line, the curve would not match up. It also doesn't look like x-axis symmetry. This is a weird one. This is actually origin symmetry. So if you can't see it, it's symmetry about a point, meaning that if we folded it twice, the section up here would match up with the section down here, and the section up here would match up with the section down here. That's kind of how I visualize this in my head. But really, it's like we take any ordered pair, switch the sign of the x and the y, and it ends up down here. So this maps to this, something over here would map to something down here, etc. If we go to the table, we'll be able to see this. So if we do negative 2 goes to 0, and that's not a good example. Negative 1 goes to 3. If I switch both of the signs, 1 should go to negative 3, and it does. Negative 3 goes to negative 15, so positive 3 should go to positive 15, and it does. Okay, so I'm going to write those down and write that this is origin symmetry. All right, last one, y squared equals x plus 4. That's going to be weird to graph because our graphing calculators only say y equals. They don't have a y squared equals. So if we square root both sides, we get y equals, remember, we initiated the square root, so we have to put a plus or minus in front of our answer. And our calculator also doesn't have a plus or minus button. So instead, what I'm going to do is I'm going to use y1 and y2. So we have square root of x plus 4 and the negative square root of x plus 4. If I graph this, it's going to graph it in 2 different colors, but I'm going to think of this as one graph. So this does not pass the vertical line test, right? You can see if I kind of think of this as a vertical line going across, it's touching more than one spot of the curve at a time. So this is not a function. We'll come back to that later. But does it have symmetry? It looks like it might have symmetry on the x-axis. If we go to the table, now because it's 2 different graphs, it's showing in 2 different spots. But what this means is that negative 3, 1, we switch the y value, it goes to negative 3, negative 1, and that's true. So this is x-axis symmetry. And let's see, what did I say? Negative 3, 1 goes to negative 3, negative 1. That's another example here. 5, 3 goes to 5, negative 3. So that's where certain points map to other points because of the symmetry, right? That brings us to example 5, absolute value. We're flying through a ton of different topics today. Good review of Algebra 1, Algebra 2 concepts here. Sketch the graph of y equals the absolute value of x minus 1. All right, if we look at the formula for absolute value, it looks like this. A times absolute value of x minus h plus k. So in this question, we want to know what is A, what is h, what is k. There's nothing in front, so the A is going to be 1 because it's like 1 times whatever. The h is actually positive 1, even though it has a minus right here because the h has a minus in front of it. So the 1 is the h, and there's nothing added on the end, so k is 0. So that means our vertex is 1, 0, and our slope for our absolute value is a, which is 1. All right? The vertex is h, k. All right, so we're going to sketch this. So we're going to put a point at 1, 0. Then our a is positive, so it's going to open up with a slope of 1. So remember, for slope, it goes up 1 over 1, up 1 over 1, up 1 over 1. And we do the same thing this way. All right, and that is our absolute value. If you wanted to do this on the calculator, you could go to Math, over to the Num tab, and it's number 1. ABS stands for absolute value. The bars even show up if you have a TI-84 plus, and you can type it right in there, okay? And that graph's going to look just like this one that we sketched. All right, we've got a couple more questions to get through. Let's take a look at example 6 about circles. Find the equation of a circle with a center, -1, 2, and a point 3, 4 that lies on the circle. If we think about what that means, we've got a center point and then some point on the circle. In order to fill in the equation of a circle, we need an h, we need a k, and we need an r. Because if you remember, the formula is, and let me pull it back up so I don't mess it up. The formula is x minus h squared plus y minus k squared equals r squared. Okay, perfect. So now we need to be able to fill that in. H and the k are the x and the y value of the center, but we already have that. What we don't have yet is the radius, but we have a point that lies on the circle, and we have the center point. So hopefully you can see that the radius is the distance between those 2 points. Now, if only we had a way to find the distance between 2 points. The distance formula, right? We covered that before. Hopefully you were thinking that. So distance equals the square root of, in this case, it's going to be x2 minus x1, so 3 minus -1. I'm just going to write it as 3 plus 1 squared plus y2 minus y1, so 4 minus 2 squared. All right? So we have 4 squared plus 2 squared, so 16 plus 4, so it's going to be square root of 20. So r is root 20. That square root can be simplified, but I'm going to leave it because I'm looking ahead and I know that my r is about to be squared. So the square root and the square are going to cancel out anyway. All right, so now I have the h, the k, and the r. I'm going to plug them all in. We have x minus -1, so plus 1 squared plus y minus 2 squared equals square root of 20 squared, which is just 20. And just like that, we have the equation of the circle. Now, our graphing calculator is not going to be able to graph this. We would have to solve for y equals, plug it in as 2 different equations, and then it could graph the upper part and the lower part separately. If you go to Desmos or some other more complex graphing software, you will be able to graph this. And I promise you, it'll look like a circle with a center at -1, 2 and a radius of the square root of 20. Example 7, finding zeros. Find the zero of each function. All right, so the zeros are the x-intercepts. It's when y equals 0 or when f of x equals 0. That's another way of saying it. So all we're going to do here is set this equal to 0 and then solve for x. And this is going to require some factoring. So whatever method you use to factor a quadratic, you need to do here. What we're going to get is 3x minus 5 and x plus 2. Again, if you are having issues factoring this, bring it up in class or come see me in office hours or email me, because I want to help you. But actually, the method of factoring is not part of our specific curriculum. So I'm not going to be able to break that down for the whole class as a lesson, but we can do it individually if you need it. Just let me know. So now we're going to set each of those factors equal to 0 and solve for x. So we get x equals 5/3 and x equals -2. All right, I'm going to do the same thing for letter B. In letter B, we have 0 equals the square root of 10 minus x squared. I'm going to square both sides to get rid of the square root. 0 squared is still 0. I can subtract the 10, divide by -1, and then I'm going to square root. Now again, just like we said before, I'm initiating the square root, so I'm going to have to put in a plus or minus. And 10 is 2 times 5, so there's no way to simplify that radical. That is our zeros, plus or minus root 10. So there's technically 2 of them, positive root 10 and negative root 10. And that brings us to letter C. 0 equals 2t minus 3 over t plus 5. Okay, so here's the deal. When does a fraction equal 0? And the answer is when the numerator is 0. 0 divided by anything is 0. The problem comes in when the denominator is 0. So when we're dividing by 0, the answer is undefined, right? You can't divide by 0. So what we need to do is just solve the numerator and then check the denominator. And that's what we're going to do right now. So we're going to do 0 equals 2t minus 3, add 3, divide by 2. So we get 3/2 equals t. And we need to check, does 3/2 make the denominator equal 0? 3/2 plus 5 is definitely not 0, so it works. All right? If we had 0 in the numerator and the denominator, that wouldn't be an answer. Example 8, vertical line test. Use the vertical line test to determine whether the graphs represent a function. Letter A, f of x equals plus or minus root of x plus 1. All right, so we're going to look on our graphing calculator. Now, again, we don't have a plus or minus button, so we're going to have to do this as 2 different functions. Negative square root of x plus 1. Okay, graph. And you should be able to see here that, remember, the vertical line test means I can take a vertical line, brush it across the graph, and if we touch 2 points on the graph at the same time, this is not a function. So this is not a function. I'm going to do a quick sketch just so that I remember why it wasn't a function. This looks something like this. And if I draw a vertical line, there it is touching twice. So that's no good. All right, let's take a look at letter B. We're going to graph 1/4 x plus 1, x minus 3, x minus 5. Okay, that's a pretty standard polynomial. There's nothing in this equation that's telling me that anything bad would happen here. So this is going to be a function. It passes the vertical line test. And the last one. Okay, now we have a piecewise. So in a piecewise function, you might remember that. The first part tells you part of the equation, and the second part tells you when that is true. So whenever x is less than or equal to 0, this is going to be the y values. This line is going to be what we have. Whenever x is greater than or equal to 2, then we have 2x minus 3. So on my calculator, I'm just going to graph both of these. Negative 2x plus 1 and 2x minus 3. It's really raining outside right now. I don't know if you can hear the rain on the roof, but I can't. Okay, so there's our negative 2x plus 1. And there's our 2x minus 3. Okay, so here's the deal. Right now, that looks like it doesn't pass a vertical line test. But remember, this is a piecewise. It only uses both of these lines at certain points. So I'm actually going to try to sketch this. And the negative 2x plus 1 is only the case for x is less than or equal to 0. So that's going to be starting when x is 0. And I'm looking at the graph to see that we're at 1. And what's our slope? Negative 2. So it's going to go up 2 over 1. And then it's going to keep going. So that's that part. It stops here, though, because that's, think along the x-axis. When x is less than or equal to 0, that's all up to here like this. 2x minus 3 when x is greater than or equal to 2. So that's the red line. I'm going to go to the table for a second. When x is 2, the red line's at 1. And then when x is 3, the red line's at 3. Because we have a positive slope of 2. Yeah, so it's just going to keep going like that. Okay, so even though this is what both of the lines look like, this is our graph. Hopefully that makes sense. Piecewise functions are tricky sometimes, but if you can kind of keep straight that this is the part of the domain where we do this, and this is the part of the x values where we do this, hopefully that makes sense. We'll see some more examples of that in the next couple lessons. But now that we have an actual sketch, you can see that this is a function. There is no point where a vertical line would touch this more than once at a time. All right, that brings us to example 9, increasing and decreasing functions. Find the increasing or decreasing behavior of each function in interval notation. All right, so let's take a look at this. X cubed, I'm going to take a look at the graph. And this is actually increasing always, right? If we could think from left to right, this curve is always going up. Even though it gets pretty close to 0 here, it still continues to go up. So we're going to write this in interval notation. This function is increasing for all x values from negative infinity to infinity. And that's all we have to do for that one. Let's take a look at letter B then. X cubed minus 3x. Okay, so this one's a little trickier. It's increasing, and then from left to right, it starts decreasing, and then it starts increasing again. So I could do kind of a rough sketch of that, if that might be helpful. Looks something like this. And I need to figure out what is the x value there and what is the x value there. I can do that on my calculator. If we go to second calc, so second trace to the calculate menu, we're going to go to maximum. We're going to find a maximum, so I'm going to go a little bit to the left of the maximum here and press enter. And a little bit to the right and press enter. Calculator thinks that we want to guess, but we don't, so we just press enter again, and then it found it. The maximum was at -1, 2. And I'll just tell you, if we did that again for the minimum, this one would be at 1, -2. All right? So for the increasing, decreasing situation, we only really care about the x values, right? We're talking about the domain. So it's increasing from negative infinity until an x value of -1. Then it is decreasing from an x value of -1 to an x value of 1. And then it starts increasing again after that from 1 to infinity. All right, so don't get tricked by these y values here. We're only worried about the x values for increasing and decreasing. So it's increasing at -1, it switches to decreasing until 1, and then it's increasing again. Maybe you even want to drag your pencil or your pen along the x-axis so that you can tell Those are the values that we want to write down, not the y values. Don't include the 2 and the -2 here. Those might be the maximum or the minimum values, but they're not part of the domain where we're increasing or decreasing, all right? Okay, that brings us to example 10. This goes to 12, so we're almost there. All right, example 10, approximating a relative min or max. Use the calculator to approximate the relative minimum or maximum. Great news, we just did that. So we already know the buttons to press for this. So let's take a look. For this first one, we have 3x squared minus 4x minus 2. Okay, so this is pretty straightforward quadratic. It's going to have a vertex that is a minimum. So we do a left bound a little bit to the left of the minimum, a right bound, and then we just skip guessing by pressing enter again. And we've got a relative min at 0.667 comma negative 3.333. So we're going to use the calculator for this. And we could have figured that out by hand though, right? Because didn't we already talk about that the x value of vertex is negative b over 2a? So if we did that here, I bet we would get that same thing and probably even a more exact answer, a fraction instead of a decimal. But that's okay. Let's try letter B. All right, we've got an upside down parabola now, upside down U shape. So we're going to go to maximum, a little bit to the left, and a little bit to the right. And we have a relative maximum, 2.50, negative 3.75. So there you go. There's two examples for you, okay? Next up, average rate of change. Find the average rate of change of f of x equals x cubed minus 3x between the following intervals. And we are going to go from -2 to 0. So all we need to do here is figure out the ordered pair for each of these. So if I plug in -2 in here, we get -2 cubed is 8, -8, minus 3 times -2. So it's -8 plus 6, going to be -2. And 0 minus 0 is 0. Okay, so we're going to plug that into the slope formula because average rate of change just means the slope between the 2 points. So we go to m equals y2 minus y1 over x2 minus x1. Plug it in, so we're going to get 0 minus -2 over 0 minus -2 is 2 over 2, which is 1. And then we're going to go from 0 to 1 for part B. So we already found that the point at 0 is at 0, 0. At 1, we plug in 1 for x. We get 1 cubed minus 3 times 1. So 1 minus 3 is -2. And then we plug that into the slope formula. We get -2 minus 0 over 1 minus 0. And that is -2. Basically what we're doing, I think I showed you an example of this before. But let's say we had this point and this point that we were studying. We're finding the slope between those 2 points like this, the slope of that line, but that's telling us the average slope of the curve between those 2 points. Okay? Last example, even and odd function. We're supposed to determine if each function is even, odd, or neither. This is really just another way of asking what's the symmetry, right? We said that if a function is even, it has y-axis symmetry. If a function is odd, it has origin symmetry. So that's all we're doing here. If we look at a table of values here, you could type this into your calculator and check for yourself. You'll see an example like -2, -6 maps to 2, 6. So that means once you look at that and a couple other examples, this is origin symmetry, which makes this an odd function. Letter B, x cubed minus 1. If you start to look at the ordered pairs for that one, which I'll pull up real quick. Oops. If we look at the graph first, you'll see that it's definitely not y-axis symmetry. It's not x-axis symmetry. It doesn't look like origin symmetry either. It would be symmetrical about maybe this point, but not the origin. If we look at the ordered pairs, you'll see that -1 goes to -2 and 1 goes to 0. Okay, so already you can see we're not mapping to like opposite versions of numbers, like a positive and a negative version. So this is going to be neither. And x squared plus 1, if you take a look, -2, 5 maps to 2, 5. It does look like our old friend y-axis symmetry, if you take a look at the graph. And that makes it an even function. All right, so that's it. That's all of our notes for lesson 1.3. Let me know if you have any questions, please, please, please. I know that was a lot, but you have a worksheet to do on Schoology, and make sure you also turn in your handwritten copy of the notes. Thank you very much, and have a great day.